Okay, let's go to the next part of the lecture 8, that is 8A2. Let me share my screen. Share screen. Okay, so this is lecture 8A2, something that you are already familiar with. So this is an opportunity to actually look at possible confusions or the fundamentals, how to solve these problems already. This is specifically first about motional EMF. Let me start with something that you are familiar with, that is the electromotive force. Okay? And most often we call it EMF. First thing to notice is that's a misnomer. Simply is not a force at all. Okay? But it has this EMF has acquired a life of its own, and hence we will stick with it. So the force per unit charge, okay, can be from the source or from the electric field that you have seen. So the total force can be both from a. So in a current circuit, there are really two forces involved in driving current, as we have already discussed partly in the last lecture. So the source Fs for source, S for source, which is ordinarily confined to one portion of the loop, let's say a battery, okay, a solar cell, or some kind of generator, okay. So it could be anything, okay, but which provides the force to inject charges into something, okay. The electrostatic force E, which serves to smooth out the flow as we had discussed, okay, and communicate the influence of the source to distant parts of the circuit. So, source for the force is to force the charge, and then what is the E, the electrostatic force? That's role is to smoothen out and carry the information throughout the circuit. So let's say a common circuit. There is a battery, and then you have connected, let's say, bulb, and the wire goes like that. So let's see what happens towards the bend. If it uses this example quite effectively, okay? So how this smoothing out helps. So this is forced here, and then let's focus on this bend, let's say, and this shown here, okay? So there is input current coming in and output current going in. So suppose there is a pile-up, okay, of charges coming in, and there is a plus pile. So that will immediately form an electric field. It means so the charge piles up at the knee, and this produces a field aiming away from the kink, if there is a kink. And this field opposes the current flowing in, okay, slowing it down because there is already a pile up, and promotes the current that is flow out, speeding it up. So until these currents become equal. So who is playing the role? The electric field that happens because of instantaneous pile up. Okay, so it will prevent the charges coming in because there is a pile up, and it will speed up this, and ultimately it's a smooth flow. That's the idea. Okay, so the static E keeps the current uniform in a circuit. That's something that I had discussed it in the last lecture as well. So the line integral of F around the circuit, okay, then we can write down is EMF, total F or dl around the circuit. The total F is the field due to the per unit charge from the source plus the electric field. All right. So, and that is equal to only the source dot dl. Why? because the electrostatic force, as you've seen, cannot produce EMF because the electrostatic force dot dl is equal to 0. Okay, so EMF is only due to the source, okay, Fs dot dl. This we already know because del cross is 0, and hence it's path independent. If it is around a total circuit, then it is 0. Okay, so this is the electromotive force, EMF. Actually, as we said, is line integral of a force, not a force by itself, per unit charge. But sometimes people define it as work done per unit charge by the source. The total work done in any way is by the source. Okay, and that is the electromotive force, or we'll simply call it EMF. Okay, so now let me illustrate, take an example. Is a problem in the book. That is, electrostatic fields do not result in EMF. Okay, so let's take this example. Okay, there is a plus signal, is a capacitor. Let me describe it here. So a rectangular loop of where is situated so that the ended height is h. This is h. All right, is between the parallel plate capacitor oriented parallel to the field E. All right, the other end is way out. Okay, where the field is certainly 0, very far away. So the question is, what is the EMF in this loop? Okay. So, and if the total resistance is R, then what is the kind of current that flows? Okay. So this is a capacitor. So basically, we're putting a loop into the capacitor with a resistor, which is, or the loop which is far out with 0. So this side is 0, and there is a field drop here. Okay. And you know the field drop. Field drop is sigma by epsilon naught. Our field here is and the height is h. Okay, and there's a constant field. So the possible answer is that E means sigma by epsilon naught into only this arm contributes. Okay, and hence sigma by epsilon naught into h is the EMF. Now that's a simple but wrong. Okay, why is that? Precisely because what we said, since the situation is electrostatic. Okay, and for electrostatic, we know E dot dl is equal to 0. Okay, so how is it that? Why is it not sigma epsilon naught h? And how is it that it becomes E dot dl is equal to 0 here? Because the field is 0 here. But remember, the field is 0 here, the field is there, but that doesn't mean that there is field and you're coming out means there is field somewhere in between also. And that field is not really vertical. Okay, as it's, and hence the solution is a fringing field at the edges must be present. Obviously it is present. And the fringing field is evidently just right to kill off the contribution from the left end of the loop. And hence this is still the paramount law. Okay, and electrostatic field, that's why cannot give you an EMF. So the answer is that current Rn is 0. So wherever there is an electrostatic potential difference, that doesn't mean you can drive current. Okay, for that you require a EMF producing source, not just electrostatic field. That difference is what we're trying to bring forward. Now let's take up the motional EMF. You are familiar with it, I know. But so let's try and understand what is the physics. Okay. So that's the physics of a generator, motional. Okay. But remember, this origin is in Lorentz Force. There's really no new physics in motional EMF. Okay. That's the point that I want to make. Let's do it in several steps. So of course, E is F mag by del dot dl, and let's say this is the situation. This is the situation that we're familiar with. Uniform magnetic field, let's say going in, and there is a uniform circuit, and there is some appliance. Okay, to could be a heater, could be a bulb, and you are trying to cool this. Okay, and so there is a relative displacement with respect to the magnetic field, and hence there is a change. So we know you have done such problems. Let's understand this. So what is the magnetic force? There is of course QVB on this arm, and that is the magnetic force. Okay. Now, although the magnetic force is responsible for establishing the EMF, it is certainly not doing any work, because magnetic fields never do any work. Okay. So who then is supplying the energy that you are getting at the heater that heats up the resistor? Okay. Obviously, the person or the agency who is pulling that, okay, is the one who is doing the work. All right. So let's understand this in terms of the details of the physics. Okay. So if it's pulling, then you can think of the charge, okay, in this arm has two velocities. Okay. One is going in this direction, okay, vertically. So that is u, and the speed with which it is being pulled is v. So it has a resultant field which is w. Okay. And what is the magnetic field force? It is of course perpendicular to W, and that is why it doesn't do any work. But it is the angle between U and W is theta, and that is the angle between the F max, okay, and the pulling force, and that is also theta. And how much is this? This is of course U, then UB. All right. So with the current flowing, okay, the charges in AB, okay, have a vertical velocity UV in addition to the horizontal velocity V. So accordingly, the magnetic force as a component through UV to the left. Okay, UV is per unit charge. Okay, and so to counteract this force, the person pulling on the wire must exert a force per unit charge, which is a pull. It must be also UV. Everything is per unit charge. Okay, and hence the particle is actually moving in the direction of the resultant, right? The W. So is moving. So instead of h, it actually travels h by cos theta. Okay, so the distance it travels is h by cos theta. Okay? And hence I can work out the F pull dot dl. That is, of course, UB is the component, and the distance traveled is h cos theta, and F pull dot dl, because this is theta, that gives you a sine theta, and that is nothing but VBH. Okay, and that is the electric field. Of course, we could get it from the flux rule, and that is we know. So the work done per unit charge is exactly equal to the EMF. That's important to know. Okay, we can do our famous flux rule: E minus d phi by dt, dH by dx by dt plus d, and is in the minus direction, and hence it is VBH. To just make it complete, we can do the analysis as you are familiar. Okay, this is called the flux rule and EMF. I'm calling it a flux rule, as does Griffith. He's saying this is not Faraday's law. This is merely a flux rule for taking care of the Lorentz force, okay, in the circuit. And the circuit structure is such that you are getting useful work done, but if the magnetic force is not the person that is doing, the agency causing the motion is the one who is causing EMF. Okay. So this is at any instant, if I take a picture, okay, then of course it is at X. And so there in the last slide, I was doing it, I was following the charge in the circuit. Here it is one instantaneous picture. Okay, the height is h. At that point, it is x. Okay, and as we know, we can work out the we can make the flux b through the calculate. Okay, so this E minus d phi by dt, and for that we can define phi is equal to b dot dA. There's a magnetic flux, and we can calculate E minus d phi by dt as minus bh by dx dt dbh. That's exactly what we've done. I'm just so for the rectangular loop, of course, phi is equal to bhx, and then that is how we got it. As the loop moves, the flux decreases in this case, and the EMF generated in the loop is minus the rate of change of flux, and that is what we have done. So this is the flux rule for motional EMF. Okay? This is for the problem, but we should be able to generalize this. This is a particular case. We should be able to generalize this. Okay, and let's do that. So let's do a formal derivation. Okay, so this is what we want to obtain. This is the flux rule for EMF. So what is in fact, the loop need not even maintain a fixed shape. Okay, and it is valid. This flux rule is valid even for non-rectangular loops moving in arbitrary directions through non-uniform magnetic fields. All right. So let's create to take care of this generality. Let's create an arbitrary loop. Let's say this red is the loop, and that loop encompasses the surface S. Okay, and that is moving in time dt. This is at time t to this. So it is stretching and is moving arbitrarily to at t plus dt. Okay, and we will follow. Let's say a point 1. And this so in if you look at between t and t plus dt, it will carve out this loop will carve out a sort of a ribbon. Okay, around the because of the motion. All right. So we will concentrate on that. So let's look at focus on point P. Okay, and it moves to P prime, from P to P prime, from P to P prime. I've even just made it even larger here, from P to P prime. Okay, so this is the dl. So the v is the velocity of the wave, and u the velocity of the charge down the wave. So the resultant is again just like in the last example, is a, let's say w is v plus u. That's the net velocity of the charge p. All right. So and this is the angle theta. So I'm just generalizing the last example to any arbitrary. But what is important to emphasize is that the physics behind the flux rule is Lorentz force. It's nothing new. We know Lorentz force, and this is only taking care of how we can get the EMF out of Lorentz force because of the motion. All right. So the change in flux after a short time dt, we can always write down as d phi at t plus dt minus phi p, and that will be because of the flux only in the ribbon, the phi of the ribbon. So what is b dot dA in the ribbon? If we calculate that, then we get the d phi, right? So the infinite small, so let's look at a small strip, infinite small element area on the ribbon. Okay. That is, of course, dA, v cross dA, dt. Okay. So that is the area. So if that is the area, then that will translate to d phi by dt is b dot v cross dl. D phi. Okay. So d phi, and that is dA. So d phi by dt is this integral of v dot v cross dl. Right? But we know that the resultant W is V plus U, and of course that W is parallel to DL all the time. So that's the way the charge is flowing. All right. Hence, I could as well write it down in terms of W. So W cross DL. So B dot W cross DL. So all I need to do is now this is the triple product. Okay. So I can rearrange the triple product instead of B dot W cross DL. I can write down as minus W cross B dot DL. All right. So that will give me d phi by dt is minus W cross B dot dl. Okay. And that is, I can write down what is W cross B? That is nothing but the magnetic force per unit charge, F mag by dl, and this minus. And this whole thing is nothing but EMF E. Okay. And hence, we have, but of course, remember, the right-hand rule for sign consistency is to be observed. Okay. Otherwise, there is a sign problem. So in this derivation, this is d phi by dt minus E. So in this derivation of the flux rule, we have assumed there is a single value. Let me make it clear. Okay. And it can move, stretch, rotate, or even distort continuously. But what you should be aware of, what you cannot do in this, include this in this derivation, is switches in it. Okay. Or sliding contacts which slide and make varying paths, or the conductor suddenly changes its size and extension so that there is a varying current path. That's not allowed because it has to remain only flux. Okay. So one has to keep, otherwise any kind of change of shape or movement is allowed to be able to use the Lorentz force in this flux. All right. So let's look at the simplest example of flux. We have done enough examples of. Okay, now let me take up the famous example of a Faraday disk. Now, what is a Faraday disk? It's a rotating metal disk and in a constant magnetic field B, and such that you can tap the EMF produced from the center and the edge by a contact like that. All right, let's describe that. A metal disk of radius A rotates with angular velocity omega about a vertical axis through a uniform field B pointing up. A circuit is made by connecting the end of a resistor to the axle to the other end by a sliding contact, which touches the outer edge of the disk. Now, the problem is to find the current in the resistor. Now, that's quite simple. So, let's say, calculate the magnetic force per unit charge on a charge here, and that is V cross B. And V is omega S phi. Okay. And B is in K direction, and hence this is omega S B S cap. That's quite simple to obtain. And so what will be the EMF? EMF would be integrating from 0 to A, this F mag dot SDS, right, along this path. And so omega B SDS is half omega B A square. And so what will be the current? Current would be E by R, omega B A square by 2R, current flowing in this resistance R. So that's simple enough. The point that I want to raise is, look, this is, does the flux or well-defined circuit make any sense here? Is there even a well-defined path in which the charge is moving in this? Though the name is Faraday disk, the physics behind here is Lorentz force is good enough to explain this, right? This is just the Lorentz force per unit charge. So, and that's enough to do that. And I can ask you to do, or you might have already done, how about instead of this, there is a rotating metal rod of length A instead of the disk above. All right. So these are all examples of motional EMF. And I'll stop here and we'll take up next the actual Faraday effect.